morning class. Today we are here to discuss about operational amplifier basics. So I am Shireen, assistant professor from the Department of Physics and Electronics, RBVRR, Women's College, Hyderabad. So what is an operational amplifier? What is an IC of operational amplifier? And what are the practical applications we are going to discuss? So operational amplifier. This is the topics. These are the topics we are going to discuss in this class. Operational amplifier. Operational amplifier is also known as op-amp. Is an integrated circuit which can be used to perform various linear, non-linear, and mathematical operations. An op an op-amp is a direct coupled high gain amplifier. You can operate op-amp both with AC and DC signals. An operational amplifier is basically a multi-stage high gain direct coupled amplifier with two differential inputs and a single ended output which uses feedback to control its overall response characteristics. So this is the diagram of the circuit diagram of an operational amplifier. As we have discussed, it is going to have two inputs, non-inverting input and inverting input, and the output terminal. Let's see what is the block diagram of op-amp. Block diagram of op-amp consists of many stages, that is, it starts from input stage, intermediate stage, level shifting stage, output stage. The input stage is a dual balanced output differential amplifier which provides most of the voltage gain of an amplifier and also establish the input resistance of op-amp. Intermediate stage is a dual input and balanced output differential amplifier. DC voltage at the output stage will be above ground potential due to the direct coupling. Therefore, the leveling stage is used to shift the DC level to zero. The output stage is usually a complementary push-pull amplifier which increases the output voltage, swing, and current supplying capacity of an op-amp. It also responsible for establishing low output resistance of the op-amp. Then let's see what are characteristics of ideal operational amplifier. An ideal operational amplifier would exhibit the following electrical characteristics, that is open loop drain voltage drain, that is A naught is infinity input resistance Ri, so that most almost any signal source can be derived and no loading of the preceding stage takes place. Zero output resistance are not, so that the output can be driven an infinite number of other devices. Perfect balance. The differential voltage in inverting and non-inverting terminals is zero. Zero output voltage when the input is zero. Infinite bandwidth, so that any frequency signals from 0 to infinity hertz can be amplified without any agitation. This is the reason why an operational amplifier is used in your transistor. Inverted infinite Torment mode rejection ratio, so that the Torment output Torment mode noise voltage is zero. Infinite slew rate, so that the output voltage changes simultaneously with the input voltage changes. Zero drift of characters with the temperature. So when the temperature is changing, there is zero drift. When you see an operational amplifier can be operated as differential amplifier. So what is differential amplifier? A differential amplifier is an analog circuit with two inputs V1 and V2 and one output V0, in which the output is ideally proportional to difference between the two voltages. That is, we write the differential amplifier as V1 minus V2. That is, differential amplifier amplifies the difference between two input voltages but suppresses any voltages common to the two inputs. So the formula for a simple differential amplifier is V0 is equal to AD into V1 minus V2. What is V1 minus V2? Because it is a differential amplifier, we write it as VD. So when you simplify this equation, you will be getting it as V naught is equal to AD into VD. So when a differential amplifier is taken or any operational amplifier is taken, it can be operated in two modes, that is common signal mode and differential mode. Common mode and differential mode. The input signal to the differential mode has to be taken to consider this common signal mode or differential mode. So let's see what is the difference between the both of them. Common mode signals. When the input signal to the differential amplifier is in phase and exactly equal in amplitude, they are called common mode signals. They are rejected by differential amplifier such that V1 equal to V2. Differential mode signals. When the input signals to the differential amplifier are 180 out of phase, underline 180 out of phase, and exactly equal in amplitude, they are called differential mode signals. That is, we write it as V1 equal to minus V2. The differential amplifier will amplify differential mode signal and it rejects the common mode signal. So when we write the expression, we write it as CMRR decibels. That is, it is expressed in decibels. That is 20 log of ADM by ACM. That is CMRR is equal to ADM by ACM. What is ADM and ACM? It is the amplification of a differential amplifier in differential mode and common mode. So the ratio is said to be common mode rejection ratio. It is expressed in decimals. So when an operational amplifier is operated, it has to be operated in two loops, that is open loop and closed loop. So if you look at this picture, in this picture you see the open loop of an operational amplifier. First picture, the second picture is closed loop of an operational amplifier. Then parameters of operational amplifier: output offset voltage. When the applied input voltage is 0, the output has some voltage and it is known as output offset voltage. Input offset current. If we eliminate the output offset voltage of differential amplifier, there will be slight difference between the input current to the inverting and non-inverting of a device. The slight difference in input current is called input offset current. Output gain of the voltage gain, the voltage gain of an operational amplifier. The maximum possible voltage gain from the given operational amplifier is open loop voltage gain and is denoted by AOL. The term open loop indicates that the circuit conditions where there is no feedback path from the output to the input of an operational amplifier. Operational amplifiers are operated with negative feedback, that is, a part of the output signal is feedback in phase opposite to the input. The resultant is said to be a closed voltage gain. Then the next parameter is slew rate. The slew rate of operational amplifier is measured of how fast the output voltage can change, and it is measured in volts per microsecond. 1 micro is 10 power minus 6, right? So to measure this slew rate, we should definitely know what is frequency. Frequency is nothing but it is the function of time. Then the slew rate can be used to determine the maximum operating frequency of the operational amplifier. So we write it as F max is equal to slew rate by 2 pi V peak. If you see the operational amplifier, nowadays the operational amplifiers are manufactured with the help of IC. IC stands for integrated chips. Then the integrated chip number of operational amplifier is 741, which is a 8-pin DIL, that is UL inline IC. So when you look at this, you have an analog diagram how it can be inbuilt on an IC such that one is offset null, 2 and 3 are inverting and non-inverting inputs, 4 is minus V, 5 is offset null, 6 is output, 7 pin is plus V, and 8 pin is not connected. This is the above view of an IC 741. IC 741 is an IC in which 2 and 3 pins are second and third pins are inverting and non-inverting pins, and sixth pin raises the output. So when we take a non-inverting operational amplifier, what is a non-inverting operational amplifier? Let's see. The op-amp has two input terminals, one inverting that is minus and non-inverting that is plus. When we apply any signal to the non-inverting input, it does not change the polarity when it is amplified at the output terminal. So it is the case where the gain of an amplifier is always positive. Non-inverting amplifier has the gain which is always positive and will not change with the polarity. Then this is the diagram of non-inverting amplifier. When you see the non-inverting amplifier, as we have seen, it is a network structure. We are going to apply Kirchhoff current law. So when we apply your Kirchhoff current law, you have your RF, that is feedback resistance RF, and your external resistance R1. So according to Kirchhoff's Sudden's law, V1 by R1 is equal to V0 minus V1 by RF. Yes, I repeat the equation. V1 by R1 is equal to V0 minus V1 by RF. Let us assume the input voltage applied to the non-inverting terminal is Vi. Now, if we assume that operational amplifier is a circuit is ideal operational amplifier. So already we have seen what are the parameters of ideal op-amp. So by applying all those parameters wherever it is necessary, we will be deriving the final equation, that is VIRF by R1 is equal to V0 minus V0 minus Vi. So when you simplify that equation, you will be getting it as V0 by Vi is equal to 1 plus RF by R1. Sorry, 1 plus RF by R1. So what is this V0 by V1? Already from the train definition, it is a closed loop of train A equal to 1 plus RF by R1. This is the voltage gain of a non-inverting operational amplifier, and it is going to be always equal to 1 only when RF is equal to 0 or R1 is infinity. Yes, R1 is infinity. So this is a picture of a closed loop where gain is always equal to 1 when RF is equal to 0 or R1 is infinity. Thank you for listening. Let's continue about the inverting amplifier in the next class. Thank you. Thank you, one and all.